Yeah, good afternoon, students. The topic that we would discuss today
Afternoon.
is evaluating performance about benchmark. These two topics we will cover. Besides these two topics, I'll also address your doubts. All right. So, how to evaluate the performance? We learned that CPU perform execution of the data that is given to it. All right, and it has some cycles. We learned that it is expressed in megahertz, means million hertz, gigahertz, kilohertz. This is the unit to measure the CPU performance. And it is like megahertz means 1 million instructions per second. Those many instructions CPU can execute in a second. How to evaluate the performance? The best way to evaluate the performance is to go for real workload. Okay, uh, in daily life means like you say no projects. When you do real world projects, you actually go to a company and then you address their problem, and then you uh, try to find the solution. That is real time project. And there are dummy projects. You go to institute and everything is already done, and you just take it like that. Here you can evaluate the CPU performance by using real world data. Means now presently I am in my laptop, I'm using my laptop. I have to execute and check and verify what is the performance. This is quite difficult. Everyone can't do this. Therefore, there is a benchmark, means a standard. Benchmark is the standard. If we say that, suppose in your group, you have some 10 friends in your group. The one who get the grade always is, let us take 9.6. He get 9.6 grade. The one student from this group of 10 students receive approximately 9.6 grade every time. So this becomes the standard to compare. Okay, if suppose another student is competing with this one, then that the one who is competing has to exceed this, has to cross this, and has to achieve more than this. So this becomes the benchmark or the standard for all the other students to take up the challenge. Okay. Therefore, here with the benchmark, it is quite easy because something is already there. We have to predict the performance by using this benchmark. All right. So what is benchmark? Performance best determined by running a real application. Use of program, typical expected workload. You suppose you give 100 programs for execution to your CPU. That is real application. And then you see in 1 second how much workload it is completing. That is this examples of that. Small benchmarks and synthesis benchmarks. And small benchmarks are those small fragments of code from inside the application loop. This is using small benchmark. It is easy for architects and designers to uh, check the performance, and it is easy to standardize. Small benchmarks are easy to standardize. And what are these toy benchmarks? 10 to 100 lines. Suppose if you have a program, you wrote a Java program or a C program that has 10 lines. All right, 10 lines of code, or maximum you have 100 lines of code. And then you measure CPU performance by giving this 10 lines of code, by giving 100 lines of code. This non-trivial, very simple and easy, and that's why it is called as a toy benchmark. And it can include NQ, queen problem, quick sort. You know quick sort. uh, like quick sort, selection sort, bubble sort. If you take those sorting programs, uh, you can execute and check up the performance of the CPU. That would become the small benchmarks. Synthesis benchmarks are that are created. Synthesis means that are created and stored. So in this, examples could be you create one large application. Let us take an application to release the results of MCA students. Okay, this is a big application. You take this big application, you run it, and you evaluate CPU performance, you measure it, you record it, and then you create a benchmark out of it, saying that for 10,000 MCA students, uh, whatever the CPU cycle and whatever is its performance, all that are measured for this type of CPU for this many cycles. uh, at this much time it is giving it and completing the work, so that when you record it and when you create a sort of um, report, it would become your synthesis benchmark. All right, more benchmarks. These are the benchmarks that are created, that have been named dry stone by Beaker 84, Wiss stone, Curo and Wichman. These are their authors. These have been created in University Computer Center loop jobs by using 12 loops. SPEC benchmark. SPEC stands for System Performance Evaluation Cooperative. This SPEC benchmark are of different versions: 89, 92, 95, 2000, 2004. These are also some of the benchmarks that have been created. When you go to their website, you can find these benchmarks. Application oriented benchmarks are those that are confined to a particular application. It's not something general. CPU performance, a benchmark would be spec for scientific application. Server performance benchmark would be spec web 99. This is this focus on throughput response time. Graphics performance 3D mark. Embedded computing EMBC. Okay, these are different types of applications, and these are the different benchmarks that measure, that evaluate the performance of that particular application. Other research oriented are media bench and com bench. And these spec CPU 2000, what is there in this benchmark? There are two types of benchmarks: integer and floating point. If you recall, integer are those numbers without any fraction value, and a floating point, we know there are fraction, as well as you express them in scientific notation, exponent mantissa into radix to the power of exponent. uh, Doing this, floating point operations require more CPU cycles, whereas integer operations require less CPU cycles. Therefore, this has been categorized into two types: integer benchmarks and floating point benchmarks. Suppose if you have input data comprising only of integers for a particular application like compression or FPGA or parser, these are different applications. All right, and this description. So for compression, it is for integer and it would take less number of CPU cycles when compared to floating point benchmarks, which are quantum chromodynamics for high-end applications, three-dimensional graphic library, multi-grid solver in three-dimensional potential field. These are high-end applications. These are like moderate applications. So therefore, you have got two different specifications for benchmarks. Look at here, this is spec synth 2000. What is the benchmark 164.gzip? This reference time is 1400. And what is the language? The code was written in C language. And what is the task purpose of this? It is compression. And the description is it compresses a TIFF, a web server log, binary program code, random data, and a tar file source. These are the different types of files that can be compressed using this, and this is the benchmark for compression. Suppose if you are doing compression, uh, you write a compression code in C language to perform all these tasks, then you can compare yours with this. This is the benchmark for that. Likewise, you have for different application classes like word processing, combinatorial optimization. This is field programmable gate array circuit and all. This, if you go through, you'll understand there's nothing in that. It's just different application classes. Here also, this is written in Fortran. Fortran was formula translation. It was an older language before 2000. This language, not only before 2000, in 90s, 1991, 92, like 80s, 90s, this programming language was quite prevalent. Later, after Fortran, when C became very popular, so everybody switched to C. So these are some of the applications that have been written in Fortran language, and this is their class in the task. They are doing some kind of application, and applications have been divided into classes. Uh, to which this benchmark belong to which class, that is mentioned here, and what does it do? All right, please go through this, you will understand. And arithmetic mean versus geometric mean. In this, the problem.
Ma'am, few students wants to join the class, ma'am. Will you
Okay.
accept them?
Yeah, sure. All right. Next, how to combine the normalized results. When you get for floating point numbers also, we did normalization. He said that this number should be 0 point and first digit of fraction should be a number, non-zero. It should be greater than 0. Like that, for that purpose, you have normalized it. You have increased the exponent value, increase or decrease based on the sign, position, and all. That is known as normalization, bringing it to some standard form. How can we normalize? How can we normalize the results? When arithmetic mean applied to the normalized execution time, A is 5.05 times faster than B. B is 5.05 times faster than A. This is used in spec ratio. This is the spec ratio. Result is strongly affected by choosing reference machine. Obviously, no, if you have a high-end machine and if you have a low-end machine, this high-end machine has got a very high-speed processor with lot of memory and other components in it. This one is like a very low configuration machine with a slow processor and less memory. You can't compare the performance of these two. When you run an application, on this machine, obviously the time would be far less than this. If it takes 1 minute, suppose if it takes 1 minute here, it might take 1 second. So directly, without direct comparison cannot be done. Okay. Students, please 1 minute. Okay, sorry about that, students. So directly you cannot compare. All right, there should be some other way of comparing. There should be some standard notation to compare the time, execution time, without any reference to the machine. It should not be machine dependent. If it is machine dependent, um, when you would like to compare, the two machines must be of same configuration. Otherwise, uh, comparison cannot be done. Therefore, you you have to use some relative results. Okay, and that is done by this geometric means. And this is measure the workload and weight by their frequency of execution. Like you assign units instead of 1 second or 1 minute. When you analyze the program, if suppose program has 10 lines, what you do is for first line it takes 1 unit of time. This unit is now dependent on the machine, but here when you say unit, it is independent of the machine. If you put seconds or minutes or time, then it becomes dependent. If you don't put any such thing, it is independent. So 1 unit, you are just saying 1 unit. It takes 1 unit, irrespective of the machine. And if there is a loop, it would take 5 units. Suppose if you say I is equals to 0, I less than or equal to 4, or I less than 5, if you say like this, the loop would execute for 5 times. So it takes 5 units of time. If you put second for each execution, it takes 5 seconds. Instead of seconds, you're just saying 5 times, 5 units of time. Like that, some standard measure is taken. And this Amdahl's law is one such execution time after improvement. This is equal to execution time affected by amount of improvement. This, um, you put the values in this plus execution time unaffected, execution time unaffected. Uh, so how do you achieve the speed up? To achieve the speed up, performance after improvement. Suppose you are improving the machine or improving the program. You can improve the program as well. Suppose if you say int a comma b comma c is equals to a plus b, print c. Instead of saying like this, we can just say int a comma b, print a plus b. This way we are avoiding a memory variable. Memory space will be used effectively. This is memory efficient. This code would become a memory efficient because an extra variable is avoided. Like that, you can improve software programs, or you can add a higher configuration CPU and memory. So performance after improvement by performance before improvement. That is the speed up. Suppose if it takes after improvement 1 second, before improvement it was taken 10 seconds. So this would give the speed up ratio. Okay, execution time before improvement, execution time after improvement. This is performance, this is execution time, which is equal to execution time before improvement over execution time affected by amount of improvement plus this you are substituting this value, this formula you are putting here. All right. So that way we are able to find out the speed up means how much improvement you have made. That is speed up due to enhancement E. What are you enhancing? Okay, in this law, we try to enhance. Uh, I told you, no, software or hardware, and then we measure is there any improvement after enhancement. So that is execution time without enhancement, execution time with enhancement. This E denotes enhancement. So, so that much ratio speed up would happen for that um, particular enhancement. Eh, what I did, my laptop had 1 TB of uh, hard disk and 8 GB of RAM. So I decided that the boot up time was too slow because of this hard disk. We know hard disk is quite slow. There is another new device, that is SSD. This SSD is uh, faster than hard disk. And if you have SSD and if you load operating system in SSD, then what happens? Uh, Boot up time would uh, improved would be improved by so much degree. Let us take yeah, earlier it was taking some maybe 30 seconds. Now it takes just 1 or 2 seconds for booting because this SSD is too fast compared to it. So I have included some 512 MB or no GB. I think 220 GB, 226 GB, 228 GB. I think that much memory I have added to my laptop. It has become fast. That way, I can measure. What I can measure? I can measure the performance before adding this SSD, after adding this SSD, and then whatever how much speed up improvement I got it. Okay, that is measured. Suppose that enhancement E accelerates a fraction f of the task by factor s, and the remaining of the task is unaffected, then this is the equation. Execution time of enhancement 1 minus f. What is f? The fraction of acceleration, means improvement, plus this acceleration fraction over fact, uh, factor s. How much factor? At by what factor this improvement has taken place? Okay, how much improvement you have achieved by that enhancement into execution time without enhancement. Okay, that would give the execution time uh, of enhancement, and speed up would be 1 over 1 minus f, that is fraction of acceleration plus fraction of acceleration over a factor of improvement. How much what by what factor improvement has taken place. So this is Amdahl's law. Amdahl's law. This floating point instructions improvement to run 2x, means 2 times. Uh, X is the value and 2x is double improvement. But only 10% of actual instructions are FP. Floating point instructions, as I told you, would require more amount of computations power. Integer requires less amount of computational power. It this law says that floating point instructions improved to run 2 times, but only 10% of the actual instructions are floating point. What does this implies? Uh, Floating point only 10%, remaining operations 90% operations were not floating point operations. In that uh, you know condition, in this situation, this improvement was achieved, to double improvement. But then if all floating point are 90%, 100%, all instructions are floating point, then we can't say whether it is achieving double of the improvement or not. All right. So this here also execution time new, execution time old. Or in old, how much time it used to execute into 0.9. Point 0.9 means 90% are non-floating point, and uh, plus point half into this 95% into execution time of old. This would give the execution time for new. And speed up is 1 over 95%. Uh, Overall speed improvement will be this much. It is not double, it is just 1.053 overall speed, because 90% are non-floating point. So example is given here: execution time A 10, execution time B 6. Uh, if our program runs in 10 seconds on computer A, which has 400 megahertz clock. 400 megahertz clock means what? 400 million instructions can be executed by that processor. And a program, you are writing one program, that program executes in 10 seconds. And we are trying to help a computer designer build a new machine that will run this program in 6 seconds. You want to accelerate, accelerate or improve the time that is taken for the program to execute. From 10 seconds, you would like to make it 6 seconds. This is like acceleration only, right? Improving. The designer can use new or perhaps more expensive technology to substantially increase the clock rate, but has informed us that this increase will affect the rest of the CPU design, causing machine B to require 1.2 times as many clock cycles as machine A for the same program. What clock rate should we tell the designer to target? What should be the clock rate of machine B? That is uh, required for the designer to choose in order to execute a program P in 6 seconds on machine B. So execution time A 10, execution time B 6. Okay, we want 6, and is equal to C by 1 by 2C. Here B requires 1.2 times as many clock cycles. So clock cycles by 1 by 2 clock cycles means B. This is A. If suppose A is 1 means B requires 1.2 into 1 over 400 into 10 to the power of 6. Why 10 to the power of 6? Because it is megahertz. Megahertz means it is 10 power 6. Mega means 6. Kilo means 3. Giga means 9. 10 to the power of 9 is gigahertz. This is megahertz. To 10 to the power 6 by 1 over x. This x we have to find. So seconds by program is equals to cycle by program into seconds by cycle. Cycle is the number of cycles the CPU achieves. So speed up is equals to what this has not been totally solved. Okay, so you have to solve it. Try to solve this equation and get the result. This speed up is assuming execution time unaffected, f into execution time before improvement. This is amount of improvement is equals to n, where speed up is the same operation. So 1 over 1 minus f by n plus 1. F is 0, speed up is equals to n. F is approximately 1, speed up is 1 by f. And it leads to infinity, speed up is 1 over f. Whatever f value is there, no, that the acceleration rate, that or that one. So make the common case fast. Frequency of one event may be much higher than another. Common case is often the simple case, thus easier to speed up. Okay, here the principle says that make the common case fast. If the case of speed up is common, which is trivial, um, and then it can be done easily. But if it is something application oriented, then it is not that easier to perform this. And the summary is performance is specific to a particular program. Yes, we cannot say that two different programs would have different performance, means same performance. If they would have different performance. Total execution time is the consistent summary of performance. Uh, you have to take the summary of the performance, that would become the total execution time. For a given architecture, performance increase come from increase in clock rate, yes, no. If we increase the clock rate, if suppose from 10 to the power of 3, if you make it 10 to the power of 6, obviously it increases. Improvement in processor organization, that lower CPU. Processor has to be optimized in such a manner that again cycles per instruction should is increased. Means cycles per instruction is actually decreased. Clock rate is increased. Compiler enhancement, that lowers CPI or instruction count. As I told you about this ABC program, if you write ABC, what compiler would do? Compiler would eliminate C. Compiler would convert source program to target program. While converting to target program, compiler would make necessary changes to make the program efficient. That is compiler enhancements. And because of that enhancement, it requires less number of cycles per instruction. It would execute fast. Algorithm language choice, that affect instruction count. Uh, uh, you know something, if you have a 10 lines of code, if you are very efficient programmer, if you know all the shortcuts, if you know how to make it efficient, you might write that program in just 5 lines. If you write the program in just 5 lines, the amount of time that required to execute 10 lines program would be cut short to half. Okay, so that is very important. That's why when you first you become a programmer, after you become a programmer, after you gain a lot of knowledge and insights and intricacies and all the different ways in which code can be written, later after you become a developer and after you become team lead and project lead and analyst, when you become analyst, you exactly know a lot of things you would know, and you can minimize the number of lines, you can make the program efficient, you can do so many things. So with experience, with lot of coding, you gain this knowledge. Just theoretically you cannot gain this knowledge. You have to go on writing program, and you have to use the libraries that measure the time to execute the program. And when once you do all that, you come to a stage where you can do anything. You can make it efficient. Okay, that's all about this last topic in Unit 5. Any doubts in this? Any doubts in any topic? You can ask me. Now I am open to questions. Students, have you jot down the questions that you have not gained clarity on? No, there are no doubts. Students, do you have any doubts?
No, ma'am.
No, ma'am.
Sure, everything is clear. Okay, how did you do your internal too? Okay, then in that case, I am going to stop the recording.